ionic compounds, you can identify them because first you always see what? What is the first element? It's always a metal, okay? Unless you're talking about ammonium. That's the only like oddball one. So you know that with ionic compounds that you always see, come on, the metal is always listed first and then a non-metal. For this one, we're trying to come up with the formula because it's giving the name. So it's copper oxide. So you know what would be the formula, just the elements, not like their ratio. So Cu and O, okay? The copper, iron, and chromium are the three that have the more than one possible charge. So what does the Roman numeral tell you? Tells you that copper is a +2. So remember that Roman numeral tells you the charge on the copper. So you know that this is a +2. Well, oxygen, if you look at it, it's in group 6. So it would have a, what charge? A -2 charge. So the group with the metals, normally the group number is the positive charge. With the non-metals, remember it's how many it would have to gain to make 8. Okay, so it would be 8 minus whatever the group number. And that is the negative charge on the non-metal. So you know that oxygen's a -2 or a 2-. Either way, you're right, it's fine. So since it's +2 and -2, what's the formula? So you put Cu2O2. What can you do to that ratio? You can simplify it. Okay, so remember, you always want the simplest whole number ratio, so you would just call it CuO. Okay, it would be 1 copper to 1 oxygen because of +2 and the -2. They would balance each other out. You just need one of each to make that compound. So what is MgCl2? What's its name? And this is the only way that magnesium and chlorine can actually combine because magnesium's a +2. It's in group 2. Chlorine is a negative. And so you have to have 2. So you notice in this, sorry, I'm trying to write plus and it's just not coming out. So notice that the swapping of the charges tells you the ratio. So that would be the only way that you would see magnesium and chlorine together. How about aluminum fluoride? So what would the formula be? You would just put, what would just the elements be first? Al and F. So Al, the charge is? +3. See, it's in group 3A. So remember on your periodic table, that A at the top, that is what's the group number for the metals. That's going to tell you the positive charge. Fluorine's in group 7, so negative. Right, so it's in group 7, so that means it's going to gain 1 electron in order to become stable. So in order to figure out the ratio, take the charge on the metal, tells you the number of nonmetals. Charge on the nonmetal tells you the number of metals. So it would be AlF3. That's the simplest whole number ratio. K2CO3. Now when you see one where you've got 3, but you still see that metal in the front, then you know that CO3 is a polyatomic ion. It's called a carbonate. So the first is potassium carbonate. So remember those 7. Those are probably ones that you're going to want to write their names, their charges, their formula on your little note card just to keep going back over. But when you see the carbon with a bunch of oxygens, that's the carbonate. The phosphorus with a bunch of oxygens, the phosphate. What about this one? CaNO3, parentheses 2. So this is... So notice you use the name of the polyatomic. So you don't have to worry about IDE at the end. You just use the name of the polyatomic when it's present. A nitrogen with a bunch of oxygens is a nitrate. This one.
So iron sulfate.
Okay, so this is iron sulfate. But you're not actually done here because of iron. So iron's special because it can have a what? It can have more than one positive charge. So you've got to figure out what the charge is, but if you look at your polyatomic list, the sulfates are what? So the SO4 is a -2 charge, so the sulfate's a -2, so that means that the iron has to be +2, okay? Because the positives are going to balance out the negatives, and since it's like a 1-to-1, 1 SO4 to 1 Fe, this is a +2, so you know that you have to put what in there? You got to put that capital, the Roman numeral 2 after the iron, like the copper 2 oxide at the top. So copper, chromium, and iron, those are the only three. That's what that Roman numeral is telling you. So ammonium, when you look on the periodic table, you're like, there is no such thing as ammonium. Because ammonium is the only positively charged polyatomic. So it comes first. So this one may throw you, because when you look at it, you're like, well, there's no metal here. But nitrogen with 4 hydrogens has a positive charge, like as a group. So it's the ammonium ion hydroxide. That's the OH negative. So notice in this, the ammonium is positively charged, the hydroxide is negatively charged, so the ratio they exist in is just 1-to-1. So their formula is just the simplest ratio is a 1-to-1 ratio. You just say NH4OH. So last one, lithium sulfide. So notice sulfide versus sulfate. When you see sulfide, then you know it's just sulfur. Okay, if you see phosphide, you know it's just phosphorus. Whereas if you have phosphate, then you know that you have those oxygens there as the polyatomic. So lithium sulfide, the formula would be and S. Okay, so what's the charge on the Li? Plus. Yeah, it's not +2. Sorry, +1. It's in the first group, right above sodium.
Sulfide is -2.
Yep. So the Li is +1, the sulfide's -2, so that would be. So you just swap the charges, tell you the numbers on the opposite ion. That's lithium sulfide. That's the only way lithium and sulfur can combine is as lithium sulfide Li2S. But now in the body, a lot of these ionic compounds, rather than existing as compounds, they exist as individual ions. Because when you take sodium chloride, NaCl, as a solid, and you put it in water, like when you take table salt, you put it in water and stir it up, those ions can actually separate. So they can separate and float around in solution. They oftentimes put a Q, which means it's dissolved and floating. So it's a really stable molecule, but the sodium ions can interact with water molecules. The chloride ions can interact with water molecules. So they do have this ability to be independent. They're usually not that far from each other, but they have the ability to float around instead of staying connected or bonded. So when thinking about sodium levels, they talk about Na+. Well, sodium levels have a really important job in that it helps to regulate the amount of fluid that's found outside of cells. So this, especially in the blood and in the tissues. So in areas surrounding cells within tissues, sodium is really important in this balancing. So if you ingest a lot of salt And so it might not always be sodium chloride. Like, I don't know if you've ever gone and gotten Chinese food. So Chinese food has MSG, which is monosodium glutamate. So it's also got sodium in it as well. So after eating a lot of Chinese food, you know, like 2 hours later, you're hungry again. But after eating a lot of times, for me, I'm like super thirsty. Okay. So I'm like, oh, I'm so thirsty. Even though it didn't feel like I was eating stuff that was like table salty, it still generates this big thirst. That is because of this ingestion of sodium. So you drink a lot of water, and the next day you notice that your rings, your wrists, your ankles are
Swollen.
a little swollen. And that is because that increase in sodium levels will hold water. And so you end up holding water in the tissues just underneath the skin. Slowly your kidneys will filter that out. But that's why you get this temporary edema, because of that elevated salt. So that also elevates what? If the sodium level goes up, water level goes up, what happens in the blood? It increases pressure. So increasing sodium intake is going to slowly increase pressure. This is a big concern for patients that have chronic hypertension, patients that already have high blood pressure. So what does the doctor tell them to try to do? You really want to try and avoid. You want to try to avoid high salt intake, because high salt is going to cause you to hold more fluid, and that's just going to increase the amount of blood pressure issues that you're already having. So sodium is one that is a water balancer outside of cells. You can think of it as having this effect on blood pressure, having an effect on fluid levels in the tissues. Potassium, on the other hand, potassium is actually a big water balancer inside of cells. But one of its big ones is that it's what triggers nerve stimulation in muscles. So if your potassium levels are low, oftentimes you have what? So this stimulates muscle contraction. So one common sort of complaint of low potassium levels is that they may have spontaneous muscle contraction that occurs. It's always when you're dead sound asleep, okay? And you suddenly wake up and like hobbling around the room, clutching your leg, whether it's your hamstring or your calf or your toes are all cramped up. And so what did your mother always tell you to do?
Eat a banana.
Eat a banana. So look at one of the sources. So bananas actually have a higher than normal level of potassium in them. Potassium also has an important role in regulating heartbeat. Too much potassium can actually cause the heart rate to be inhibited, so it can cause your heart rate to stop. In fact, that's what they give people with a lethal injection, is they give them a big dose of potassium chloride and it stops their heart. Not enough potassium and the heart rate will become very irregular, kind of weak and feeble. Instead of having this normal beat pattern, you end up with this like kind of half strength beat, so you don't get good circulation as well. So this cardiac cycle as well, cardiac function, potassium levels. So especially with patients that have long-term stress, that have been in the hospital, that have an infection, that have like major issues going on that has caused them to need to be hospitalized, they really watch potassium levels, because if their potassium goes too low, their heart rate's not going to be strong enough to improve circulation. If their potassium levels go too high, though, they can actually have sudden cardiac arrest. So either issue can be a major problem. Calcium. So most people are familiar with this because calcium helps to add strength and integrity to bones and teeth. And most of it, dairy. Okay, you can get calcium from whole grains. Magnesium is one that plays a role in sort of inside cell activity. You find magnesium in things like nuts and seafood. As you notice with this, in just a regular diet, you typically get enough of these. These are all those minor elements. Remember when we said like carbon, hydrogen, oxygen, and nitrogen, those are the 4 big ones. But then the ones underneath, the 6 minor, that's really where the bulk of these come in. Iron is one that is extremely specific. It's kind of like iodine. Remember we talked about iodine in chapter 2, but iron is one that's almost entirely sent where? Where do you need iron? In your red blood cells, okay? Because it's used to build functional hemoglobin, which is the protein that you find inside of red blood cells. And red blood cells are responsible for carrying oxygen. So very important for oxygen transport. If any of you have ever been anemic, then you probably know what it feels like if your iron levels are low, or if you don't have enough red blood cells in your blood. You stand up really fast and you like get like super dizzy. Okay, you're like going out, you're like, I'm exhausted. I can't do the same thing. All that, if there's not enough oxygen in the blood, oxygen's used to generate energy. So your muscle cells are not going to be able to do exercise if there's not enough iron that's present. That's all the sort of side effects of anemia. Notice chloride. So chloride is there. It is kind of the balancer. It's wherever there's sodium, chloride's usually not far behind. They're there to try and balance each other out. So the negative charged ions, they help to balance out the positively charged ions. This will be one that we're going to talk about when we talk about acids and bases. So HCO3 negative, this is called the bicarbonate. And this is very important in balancing pH in body fluids, especially in the blood. So we will talk about it again. One more. But those positively charged ions, the sodium, potassium, and calcium kind of have big jobs. Magnesium's much more cell. Iron's really red blood cell, a little more specific. But like I said, in terms of sources, as long as you're getting a regular diet, you can really get these minor elements and trace elements in adequate amount. So this leads us into the second type of interaction between atoms. What makes this different? This is when you have a molecule like H2. So hydrogen, oxygen, nitrogen, chlorine, fluorine, bromine.
Thank you.
These exist in nature in pairs. So you don't see hydrogen atoms all by themselves, but you will see hydrogen gas. You don't see oxygen atoms all by itself, but you'll see oxygen gas. It's always described as being O2. So if we think about it from the Lewis dot structure with hydrogen, remember that hydrogen's over in group 1, so it only has 1 dot, 1 electron. And in order to be stable, the first energy level needs 2. So hydrogen has 1, and so if it can get 1 more, it would be stable. But if you have the other hydrogen over on this side, and it has its electron, does one have the ability to pull an electron from the other? Does one hydrogen have a stronger attraction than another hydrogen? No, they're like the same. So they're kind of matched. Whereas with sodium and chlorine, sodium wants to get rid of its 1 electron, and chlorine only needs 1. So there's a big difference in valence electron number. Here, notice the valence electrons are basically the same. So that H. So they have the same number of valence electrons. So one atom can't pull from the other one. Instead, if they allow these electrons to sort of span the area in between the 2 atoms, then the left hydrogen will sometimes have 2 electrons and the right hydrogen will sometimes have 2 electrons. So this will give that right hydrogen stability, and the same with the one on the left. So those electrons then can go back and forth between the two. Sometimes they're both over on one side, sometimes they're both on the other, but they're that way enough to create the stable electron level. And so for hydrogen, all it needs to have is just two. So the way you'll see this drawn is an H dash with an H. So instead of having positives or negatives, the dash represents a pair of electrons. And this is a covalent bond. So this is not transferring. This is when they have what they call electron sharing. So electrons are actually sort of spanned between two atoms to create the stability. And that's the reason that hydrogen exists the way that it does. So their example is with chlorine. So two chlorine atoms. So if you look, the left chlorine, you count 7. The right chlorine, you count 7. The chlorines can't pull electrons away from each other because they're exactly the same. So they each have a strong attraction for electrons, but if they'll come closer together and allow those single electrons to spend partial time with each, that creates a covalent bond. So this pair that is shared in between is called a single bond, and they just use a dash. And you can see in this one then, it makes this chlorine have its 8. So it has the 6 that belong to it, plus the pair that is shared. And then the right chlorine has the 6 that belong to it, and the pair that is shared. So that one comes out. They look pretty reasonable. Carbon, nitrogen, oxygen, hydrogen. Remember that's CHM. Remember that's those major elements. These are the ones that really do this. Okay? Carbon, hydrogen, oxygen, and nitrogen, they have a close to full shell. So instead of being able to pull electrons away, when they interact together, they'll form these types of bonds. So you're going to find a lot of covalent bonding with molecules that contain carbon. If they don't have a metal, then you know that you're talking about covalent. And that's really always the kicker. If you look at the molecule and you don't see a metal listed first, unless it's ammonium, you know that that means it's covalent. So in looking at this, so notice carbon. So carbon, remember that's in group 4A. So that tells you it's got 4 valence electrons. So you can kind of see how it has like empty spaces. It needs 8. So it can form a pair above, below, to the left and the right, which would make 4 single bonds. But it could also make a single bond, 2 single bonds, and a double bond. So a double bond would just mean that 2 pairs of electrons are shared between carbon and another atom. This shows how carbon can actually share 2 double bonds with other elements to create stability. And then the last option is that the carbon could actually make a triple bond. That would be 6 electrons shared between 2 with a single bond on the opposite side. So there's a lot of different variations that carbon can do, and that's why carbon is the basis of organic chemistry. It's a whole sort of group or topic, 2-semester class all on itself. But because it can make all these different possible combinations, unlike sodium chloride, sodium and chlorine, 1 and 1, that's it. But with carbon, you can actually build much larger structures because of all of this variation you can have. So let's look at a couple of them. So the first one, so CH4 up at the very top. The way that I go through in terms of listing and trying to figure out how they bond is I first determine how many bonds am I going to need to make that stability. So carbon has 4 valence electrons, so it's going to need to form how many bonds to make a total of 8? Yeah. So carbon always has to have 4. But we said hydrogen, it has 1 electron, but it only needs 2 to be stable. Hydrogen never forms more than 1. So the rule is always start with the atom that needs the most bonds. So always put that like as the center one. So in this one, you're going to put a carbon. Because it needs the most bonds, kind of make it like the center. Well, can you see in this, if carbon needs 4 and we have 4 hydrogens, how do we arrange them? Just put 1 up, 1 down, 1 left, and 1 right. So you see in this then, we start with carbon. Can you see that carbon has 4 bonds? Can you see that each hydrogen has 1? And it's connected as a single unit. So this is like a single molecule of CH4. If you drew them out with the little Lewis dot structures, you could do that too. Oh, except for not that line. Just remember that a line, like I drew above, the line just represents a pair. So the blue electron would belong to the hydrogen, but it's shared between the hydrogen and the carbon. The purple electron shared between the carbon and each hydrogen. So that gives carbon its 8. It gives each hydrogen its 2. So that really allows them to behave like noble gases. It creates this stable molecule. So what about NH3? How many bonds does nitrogen need to make 8? It's going to need 3 because it's in group 5. So if you look at nitrogen, you see it's in group 5. So that means it's going to have 3 bonds in order to be stable, in order to have its 8. But hydrogen, we said, only ever has 1. So which one do we start with? So you're going to start with nitrogen. So you see nitrogen needs 3, and you have 3 hydrogens. So what do? So you just arrange them around. Now when you look at this, does it look like there's nothing at the top of the nitrogen? But if you look at, it's in group 5. So the nitrogen has 1 electron, 1 electron, 1 electron, 1 in part forming the bond. And at the top of the nitrogen is the other electrons. Nitrogen has 5. So 2 at the top and then 1 involved with each single bond. So now when you look at it, do you see the 8? So adding in those what are called non-bonding electrons or lone electrons can sometimes help you to see that total of 8. Water. You're 2/3 water. So hydrogens have, they're only ever going to have 1 bond. Oxygen is in group, so it's going to need to form 2. So you would start with oxygen. When you look at the list, oxygen needs 2, and you have 2 hydrogens, so So since oxygen's in group 6, above the oxygen is 2 electrons, and in my picture to the left of the oxygen would be 2 more. So can you see oxygen's 6 electrons, 2 up, 2 to the left, and 1 involved in each of the covalent bonds?
So it doesn't matter how you place them.
No. So you could have like the non-bonding electrons above and below and the hydrogens to the side, because these things don't lay still. So they're moving around, they're floating, especially the liquids and gases, and so it doesn't matter which order. So you could have a hydrogen up, a hydrogen to the left, as long as you have an oxygen with 2 hydrogens attached. Okay? Ooh. Did I skip one? Yes. So what about O2? Whenever you talk about oxygen, you always give them O2. You don't give them O, right? So O2, how many electrons, or what group is that oxygen in? 6. So that means that you know it's going to have 2 bonds. So in this one, they're exactly the same. So if you have an oxygen, and it has 1, 2, 3, 4, 5, 6, right? And the other oxygen, 1, 2, 3, 4, 5, 6. So notice you could pair them this way. So you make one connection, but then when you go back and count, that's all you have to work with. Okay? So if you've put all of your atoms, the atoms down, and you form the bonds, and you still don't have 8, notice the left and the right, they only have 7. So this tells you that they're going to share more than one pair. The only way to create that stability is to just move the electrons that are not paired, move them in between the 2 atoms so that they have the shared pairs. So if I do that, that's going to take these ones off the bottom. And now when you look at it, do you see that each oxygen has 4 electrons that don't form a bond? They belong to the oxygens, 4 on each side. But then there's 4 that are shared. 4 that are shared in between. So the left oxygen acts like it has 8, and the right oxygen behaves as if it has 8. This is why you see oxygen written with that double dash. The 2 dashes represents a double bond. That means that there's 4 electrons in between. And you do this if you put if you look at the formula and you put everything down. So in this one, I put both of my oxygens down and linked them. But then I see that I don't have 8. That tells you that the only way to create the stable 8 is to go ahead and pair up more. So nitrogen's another diatomic. Nitrogen's in group. So how many bonds does it need to have 8? 3. But they're each going to need to have 3, and that's all there is just N2. So if you place a nitrogen, and it's got its 5, the other nitrogen, and you're sharing, that's really all I have. I have nitrogen and nitrogen, 5 with each, and I've linked 1, so 1 pair is shared in between the 2. But now you can see that there's others that are not, so those get moved into the middle. So this one and this one move over. That creates a double bond, but that's still not going to give me enough. So you would take and move this pair and this pair. So what you end up with I just use the different colors so that you can kind of see them. Each nitrogen has 2 electrons that belong to them exclusively, but they're actually sharing 3 pairs in between. So you can see how the left has 8 and the right has 8. 6 in between plus 2 of their own. So this one you'll see drawn like this. 3 lines, each representing a pair, so that's a total of 6 electrons, and they call that a triple bond. And that's kind of like your last ditch. First, try to just lay down and do singles. If you've put all of your elements down and you have unpaired, you don't have sets of 8, then you can form multiple bonds. Carbon dioxide, CO2, so we said carbon has 4 bonds. Oxygen has 2 bonds. Oxygen has 2 bonds. So you would start with carbon. So if they were all 4 single bonds, they would just have one above, left, and right, below. But we got to put an oxygen, so it doesn't matter where you put them. We'll add an oxygen in. So oxygen's in group 6. So that's one of them. Then if you add the other oxygen, you could do a couple of things. Where could you put the oxygen? You could attach it to an oxygen, but what would that do with the carbon? Notice the carbon's got like 3 places that it doesn't have anything connected. So connect first to that main atom. So with the carbon, put an oxygen on. Since carbon needs the most number of bonds, put it on that one first. Okay, so you'll add your second oxygen, and it doesn't matter if you put it above or below, to the left or the right. And I don't care if you put the pairs this way or that way, that doesn't matter, just so long as you put them in between. So now each oxygen has how many electrons total? 7. And carbon has 6. But I've listed everything that's there. So you know that it can't just be this way. We've got to make 8. Carbon is stable with 8. Oxygen is stable with 8. So now we're going to have to double up. So you can move. If you move 1 pair between the carbon and the oxygen, take the other pair and move it. Trying to keep my dots in the same place. How's that? So the red oxygen, can you see there's still just 6 red electrons? Carbon is blue. See the 4 carbon blue dots. And then the left, the purple oxygen, you see it's 6 over by it. But when you count them, oxygen has, each one have 4 that belong to themselves and 4 that are shared, which gives them 8. Carbon has 4 that are shared on either side to give it 8. So if you drew the dash structure, what would it look like? Okay, 2 dashes on one side, 2 dashes on the other side. Oxygens. Carbon in the middle. Each dash represents a pair. But notice here we're talking about carbon, oxygen, nitrogen, hydrogen. CHM, okay? Those 4 main elements, they're all those non-metals. They don't pull electrons away from each other. They create stability by sharing. So there's 2 others in here. There's this one. This is cyanide, HCN, hydrogen cyanide. And then this one is H2O. That's formaldehyde, which is like an embalming fluid. Still pretty simple ones. So HCN, hydrogen has 1 bond, because it's got 1 electron. Carbon's going to need 4, and the nitrogen's going to need 3. So which one do you start with? So you're going to start with carbon. Always start with the one that needs the most. So which one needs the most bonds next? Nitrogen. So put it down second. So like try to link the ones that need the most bonds together first. okay? So I paired those. And I have to add one more. Add your hydrogen to the one that needs the most number of bonds. So like kind of keep carbon as the center and keep adding things to that center. So you could put it at the bottom, you could put it on the side, you could put it on the top, wherever you want. Just for space-wise, I'll just set it here. I don't care if the electrons are paired up and down or right and left, that doesn't matter, as long as they're in between. So am I done? No. But if you look, can you see that carbon has 2 that are not paired? Nitrogen has 2 that are not paired. So in that, once you've laid all of your atoms down and you see that there's pairs, that's when you begin to move them. So you'll just slide the carbon electrons between carbon and nitrogen, slide the unpaired nitrogen electrons between carbon and nitrogen. So how many bonds will that be? 3. So we'll have the pair that's already there, but we're going to move this one, and then we're going to move this one and that one. So we'll end up with 3 in between. So hydrogen won't change, not affected. Carbon will have its 3 on one side, and then nitrogen's 3, and then those other 2. I didn't even touch it. See if I can redraw my nitrogen. It got kind of crazy looking. There. So if you saw this with dashes, you would see an H, single, dash to a C, and then what? And then 3 dashes to the N. So each pair is a dash. These ones are really like the most complicated ones that we'll do. When we get into chapter 4, you'll see this and it'll become almost like automatic. But when you're looking at with oxygen and nitrogen added in, these are really the more complicated ones just because there's too many. It seems like there's more possibilities. But my rule, always put down the atom that needs the most bonds and then connect other atoms to it. Okay? And 99% of the time, you'll find that they'll all lay down just fine. So like with that one, instead of putting the hydrogen on the nitrogen, put the hydrogen on the carbon because the carbon needs the most bonds. So you put the carbon down, then the nitrogen, but then go ahead and put the hydrogen on the carbon because it has the most bonds that it'll form. So CH2O, last one, carbon needs 4, 1, 1, 0. Or sorry, not 0. 2. I was just looking at the O. So you start with which? So what did you connect to it first? An oxygen. Oh, with that line. So connected an oxygen to it next. Okay. And then? So where will you put the hydrogen? Put it on the carbon, okay? So go ahead and put them all around the one that needs the most. Put a hydrogen here. And on top, hydrogen up here. Okay? So then the last thing to do is make sure that you count them. Or they all have 8. Does carbon and oxygen both have 8? No, but I've put all of my atoms down, so that's when you end up forming more than one bond. And so in this, can you see that this one and this one, if we can move those between the carbon and the oxygen, that'll fulfill the 8 for carbon and the 8 for the oxygen? So move this one. And this one, putting them there. Now oxygen, you can see, shares 4 electrons with carbon and has 4 of its own. Carbon shares 4 electrons with oxygen, but then shares 2, one with each hydrogen, one pair with each hydrogen. giving it its 8. So in this one, I'll just spread those hydrogens out. You could have them above or below or left or right. I was just trying to keep them away from the one above. But you have a carbon double bonded to an oxygen and then a hydrogen on each carbon, on the carbon. 2 hydrogens on the carbon. So they ran into issues with the naming part. So we talked about the naming in ionic. Use the whole name of the metal, first part of the nonmetal, plus IDE. But when you have binary covalent, they had problems because they found that they could have this, or they could have this, or they could have this. Because it's sharing of pairs, you can have multiple nonmetals that can form bonds together. So you can have a covalent bond. You could have 2 nitrogens with covalent bonds, and then they're covalent bonded to oxygens. And so you can't just call that first one nitrogen oxide, because how would you tell it from the second one? How would you be able to tell it from the third one? So because there's multiple possible ways that nonmetals can form covalent molecules, they want you to use prefixes. So these are just the Greek number prefixes. If there's 1 on the front, they don't actually make you say anything other than its name. So when you see this, what do you call that? CO2 is carbon dioxide. So you notice there's only 1 carbon, but you just say its name. So you always use the whole name of the first element. If there's only 1, you just write the whole name. But then what did you have to do with that oxygen? You call it what you have in front. So CO2 is carbon dioxide. So you had to use this di. So instead of just carbon oxide, it's carbon dioxide, and di means 2. So that tells you how many oxygens. So you still use the first part of the second nonmetal. And IDE. So you're still using that same format, except that you have to add in a number prefix. You'll use a number prefix with each to indicate how many of them. So what would you call that one? NO2. Nitrogen dioxide. So N2O, first, what's this? If CO2 is carbon dioxide, CO is monoxide. Okay, so like you have a carbon monoxide detector, that's capital C, capital O. Still, this one's carbon dioxide. This one's carbon monoxide. So you have to use mono if the second element's only 1. You use di if an element has got a 2, tri if an element has 3, tetra if an element has 4. And from that, they go up kind of normal, like 5 is penta, 6 is hexa, 7 is hepta, 8 would be octa. So they're just those Greek prefixes that indicate a number. So NO2 would be nitrogen dioxide. N2O though. N2. Use the whole name of the first element plus its prefix. If it's not a 1, you have to add the prefix. So this would be, but there's 2 of them, so it's dinitrogen. Seems very strange the first few times you say them. dinitrogen, and then there's just an O at the end, so that would be, if there's only one, you have to tell how many, so you call it monoxide. The only time you don't have to name the number is if there's only one on the first element. So like CO2, you just say carbon monoxide. CO, carbon, but the second one you do have to tell if there's only one. That's why it's carbon monoxide. So what would N2O2 be? Yeah. Dinitrogen dioxide. That means there's 2 nitrogens and 2 oxygens. So here's the Greek prefixes for them. Mono is 1, and the rule with mono, second element only. You do not use mono if the first element is just a 1. Di means 2. Tri means 3. 4 is the weird one. 4 is tetra. And I remember this like Tetris. I don't know if you ever played Tetris. That was those blocks of 4. Sometimes they were all 4 in a line. Sometimes they made a square. Sometimes they made an L. So tetra, they were always blocks of 4. So tetra and 4. Whereas penta, like the pentagon, 5 sides. Hexa, like a hexagon has 6. Heptagon has 7. We don't see those ones all that much. But really 1 through 4 are the more common ones. So what we call NH3. Use the whole name of the first element. Tri. It's an H. Not hydroxide, because remember that's the OH. So you would call it nitrogen trihydride. So hydrogen, the first part of hydrogen is just hydr, H-Y-D-R. H2O, you call it water. But its fancy name, like NH3, its common name is ammonia. So it'd be dihydrogen. Monoxide. Sounds much scarier. Dihydrogen monoxide. H2O2, this is hydrogen peroxide. That's its common name. Hydrogen peroxide you put on a cut to help clean, oxidize any microbes that might be in that cut. But what would its name be according to this? You always use the whole name of the first element. First part of the second element plus IDE, but you use number prefixes to show how many. Because if I just called that hydrogen oxide, you wouldn't know how many of each. So with covalent, you have to use number prefixes because there's more than one possible way they can combine. So what would CCl4 be? No, 4 would be, yeah, exactly. Tetra, because there's 4. Chloride. We did CO2 and CO. So what's N2O5? Pentoxide. And then the last one, N2O4. Nitrogen and oxygen can make lots of combinations. There, that would be pent oxide. So usually if there's an A on the end, like tetra, you just leave it off with the oxide. So there's not 2 vowels in there. Oh, it's 4, so it should be. Sorry, I was thinking from above, so it would be tetroxide. Just like with penta, you leave it off. TRT, tetroxide. But make that as a note because that's a difference between ionic and covalent. Ionic, you don't need number prefixes because sodium and chlorine can only combine in a 1-to-1 ratio. because they transfer electrons. They're forming ions, and that's defined. But with this, with nonmetals and hydrogen, you can have multiple different combinations that they can combine in, and that is why you need to have the number prefixes. So next time what we'll do is we'll go through and I'll like mix. I'll give you some ionic and covalent to have you identify them and then be able to name them so that you can see how those differences are. It'll help to reinforce ionic and also help to bring this one back in too. So these ones are just covalent. So we did this one. So what's CBr4? Uh-huh. Uh-huh. Yep. You only have to put a number prefix on the front if it's not a 1. Okay? The first element only needs a number prefix if it's not a 1. You always have to use a number prefix with the second. I think we did this one. We did that one. We did this one. So what's the last one? I'm like, I already made those ones up. Uh-huh. Yep. Nitrogen trifluoride. Right. So here's sort of like, they use like a little, like flow charts. So ways that you recognize, I always tell people, just look at the first element. If the first element is a metal, it's ionic, right? So sodium chloride, magnesium fluoride, lithium bromide. If the first element's a metal, then you know it's going to be ionic. But if you're seeing carbon, nitrogen, oxygen, hydrogen, then you're looking at the covalent. So you see the CHN, you see those nonmetals, then you're going to be looking at covalent. If you're talking about metals that are in groups 1 or 2 or aluminum. So group 1 and 2, which would be like the sodium and the magnesium columns, or aluminum, you don't have to use any Roman numerals or anything, you just name it. Groups 1 and 2 or 3A, and really 3A is just aluminum. Then those, they're going to exist in a defined ratio, you just name it. So there's no Greek prefixes, no Roman numerals to them. If you have Fe, Cu, or Cr, if these are your metals, Fe, iron, remember, can be +2 or +3. Copper can be +1 or +2. Chromium can be +2 or +3. So because they have a way, they can be one or the other, then you're going to have to figure out what's the charge and make sure you put a Roman numeral if you do its name. Okay, but that's just those 3. There are more of them, but those are the ones that we use the most common. However, if it's covalent, then you're always going to use the Greek prefixes. Unless the element has only 1, the first element is a 1, then you don't have to put mono. Okay? A little flow chart. So we'll do that one next time. So the last thing is the shape. So these molecules, when they share electrons, these electrons here, here, and here, they go back and forth, back and forth. So this is CH4. So the electrons that are shared between carbon and hydrogen, they really go like this. And this one, this pair goes here, this pair, back and forth, back and forth. They spend like half and half. They spend part of their time with the carbon, part of their time with the oxygen to create that stability of 8. But the thing to remember is these electrons are negatively charged. So these are kind of there, they kind of have to stay close together because they're paired. But pairs don't want to interact with other pairs because they're all negatively charged. So they did studies on this and said, well, each electron pair is going to get as far apart from each other as they can because they're negatively charged. And you know that like charges repel. So we like to draw it like this. But when you draw it like that, it makes them look like they're 90 degrees apart. So when you look at it flat, but these molecules are actually 3-dimensional. So If it was flat, it would be 90. But in a three-dimensional shape, the carbon kind of sits in the middle, and the 4 bonds are spread apart in like a three-dimensional arrangement, and that's going to put them greater than 90 degrees apart. So when they first started talking about this, they said, well, can you see that this structure has 4 points, like each hydrogen is a point? And it would be as if each one had like 4 sides. So they're on the bottom, on the back, on the front. So it's sort of like there's 4 sides on this molecule. So that's how this name came about, because tetra means 4. So you can think of it as being 4 corners, or look at it as being 4 sides to it. This puts electrons as far apart as possible. Carbon with 4 single bonds always makes this tetrahedral shape. So it really doesn't matter if there's like a single bonded nitrogen above, or a single bonded oxygen down, or a hydrogen, or even a chlorine. Carbon with 4 single bonds is always going to make a tetrahedral, because it's going to have 4 pairs of electrons that want to get as far apart from each other as possible. It's always the tetrahedral. Always. But nitrogen and oxygen, they have those non-bonding electrons. They have electrons that belong just to them. Well, those electrons actually take up more room than the electrons that get shared. So in this one, you can see, where are you? Here. There's the normal tetrahedral. I said carbon with 4 single bonds. This next one, this is NH3. This is CH4. NH3, the nitrogen's in the middle, but it has its non-bonding electrons that are above. And in fact, these non-bonding electrons are like, because they belong just to the nitrogen, they require more space. So those non-bonding electrons are kind of in their little orbitals, just connected to the nitrogen. And what that does is that actually pushes the bonding electrons further down. So when you look at the 2, can you see how it looks like those hydrogens look like they're a little lower? They look like they've been pushed a little bit more than what you see with the tetrahedral. Instead of being 109.5, it's closer to like 107.5. The angle's smaller. These get pushed. That's going to create the nitrogen with its little hydrogens directly underneath it. And so they say, well, that really looks more like a pyramid. So instead of having anything above, because those electrons take up, they're kind of like hogs. They take up this space. They push the bonding pairs further apart, further away, and that creates sort of like a little shortened structure. Oxygen has 2 of these because oxygen is in group 6. So oxygen has this pair and this pair. So notice in water, that means now we've got this big group, and we've got this big group. And can you see how that pushes its hydrogen, the bonding pairs, they get pushed even further? Their angle, bond angle, for tetrahedral is 109. For water, it's only 104. So just think of the non-bonding electrons. They take up more room. And that will alter or change the shape of the entire molecule. So when you look at water, most of the time, have you ever seen it when they draw it like this? They'll draw it like this, and so like a hydrogen comes off and kind of sticks down. They're not really at 90 degrees. They almost look like they're squished a little more. And so that, because of this shape, that's why they call that bent. So oxygen with 2 single bonds always has a bent arrangement. Nitrogen with 3 single bonds always forms a pyramid, and it's because of their non-bonding pairs. Non-bonding pairs repel more than bonding pairs do. And that's going to end up affecting the actual shape of them. So in lab on Wednesday, we're actually going to work with the balls and sticks and look at how these structures are a little bit different. So in the geometry, where are you? There it is. So in the geometry, AB4, I told you this is always a carbon with 4 single bonds. It will always have the tetrahedral shape, 1 up and then 3 kind of angled down. And the angle's like right at 109.5. Nitrogen, on the other hand, they call it a slightly different form. And here's what those letters mean. So when they talk about an ABN designation, A is the center atom. The atom that like needs the most bonds, the atom you put down first. Usually it's carbon. If it's not carbon, it's nitrogen. If it's not nitrogen, it's oxygen. So it's one or the other. B is how many groups are bonded to it. So you can see with CH4, carbon is the central atom and it has 4 hydrogens connected. So they call it an AB4. Carbon would be the A, and it's got 4 groups connected. It doesn't matter if those are hydrogens or if those are chlorines or if those are nitrogens. If it's single bonds, then that's going to be 4 groups connected. Nitrogen's a little bit different because it has this. It has that non-bonding group, and that's what the N stands for. So these are the non-bonding electron pairs on the central atom. So with NH3, if nitrogen is A, do you see that it has 3 groups connected? It has 3 hydrogens connected, and then it has that one pair that's stuck just to the nitrogen. So they call that an AB3N, and that's always got a pyramidal shape. Very typical if you have nitrogen with 3 single bonds. It's going to be a pyramidal. So it doesn't matter if it's got 3 hydrogens, it could have 3 chlorines, it could have 3 fluorines. But if it has 3, because that nitrogen has that extra pair sticking up, that creates the pyramidal arrangement. The next one we did was water. So can you see how water is called an AB2N2? What's the central atom? So what would be the A in water? The one in the middle. So this is, it's an oxygen. So we have the oxygen. And so how many groups does it have connected? 2. It has 2 hydrogens. But see, it's 2 non-bonding pairs. So it's got 1 up on either corner. So that has 2 non-bonding pairs. So an oxygen with 2 single bonds would form this bent arrangement. So instead of the hydrogens being spread as far apart as they can, instead of hydrogens being straight, they're going to be pushed to the side, and it's going to create that bent arrangement to the molecule. So the last 2, this one's formaldehyde. So this is the one that we drew that was CH2O. So remember in this, if you look back at the molecules that we drew, CH2O, we put carbon first. We linked it to an oxygen. We then linked a hydrogen, and another hydrogen. But the only way we could get the total of 8 is to form that double bond. So now remember that oxygen has non-bonding electrons, but when you're looking at this ABN, carbon is the A. How many groups does the carbon have connected? 3. So you see that it's got an oxygen and 2 hydrogens. So it has 3 groups connected. Does carbon have any non-bonded electrons? Does carbon have single dots around it? No, carbon never does, because carbon always forms 4 single bonds. There are no non-bonding electrons, so notice there's no N here. So you can see how the oxygen then looks like it's pointing up, the hydrogens look like they're coming down, and so it kind of looks like a triangle. So you see that difference in shape? In fact, you can take this molecule and lay it down, because that's the furthest the bonding pairs can get from each other, and that's why they call it trigonal planar. It means a triangle that's flat. So trigonal planar, a carbon with a double bond and 2 single bonds will always form this. So if a carbon has 1 double bond and 2 single bonds, you'll have one group off and the other ones will all be at that 120 degrees so that they can be as far apart from each other as possible. It's the last one, and we'll quit. Last one is called AB2. AB2, example of this is carbon dioxide. So remember, with carbon dioxide, we start with the carbon, and we put 2 covalent bonds to each oxygen. The oxygens have their little non-bonding electrons. Those are fine. But when we talk about the AB2, we always talk about the center atom. So in this one, the center atom is carbon. Okay? So you look at the carbon, then you ask yourself, well, how many groups are connected to it? 2. So if they're repelling each other, the furthest they can get apart would be 180 degrees, like they would be sticking off. So they wouldn't be close together. They would automatically spread. The oxygens are going to want to get as far apart from each other as possible. So that's why it always looks like a straight line. So the carbon with the oxygens on opposite side, which is why they call it linear, because they say it looks like a straight line. So this is the linear arrangement. Whereas with water, you see it's bent, but that's because those water's non-bonding electrons create that repulsion. So those hydrogens can't get straight across, they get pushed over. So when you look at this one, this bent arrangement, it's different because of the non-bonding electrons. But carbon doesn't have any non-bonding electrons. So best example of AB2, carbon with 2 double bonds, like carbon dioxide. The 2 groups will get as far apart as possible and create a very linear looking molecule. So there's actually a couple more shapes, but these are the basic ones. And we actually went through the drawing of each one. This is in your book, so use this to go through and write your examples with the ones we did, because they really won't get any more complicated than the ones we did. So next time we pick up, I'll put, we'll do ionic covalent naming on Wednesday. And then we're going to finish up chapter 3 and start talking about chapter 4. The only thing we have left to talk about in chapter 3 is about moles and molecules. We have one math thing that we have to cover in chapter 3. For lab on Wednesday, so anybody that's with me in lab on Wednesday, you can do the very top part of the pre-lab for 5. But don't worry about trying to do the bottom part, because it's all chapter 4 material, so it's probably going to look really strange. But the top part, they want you to actually draw some molecules and give the geometry. So you can use this information to answer that top part, but we will talk about the bottom part specifically in lab, so don't worry about that. Okay? I think I got everybody.